You see problem 2, force acceleration 2. The spool and wire grab around its core has a mass of 20 kilograms. So when it's 20 kilograms, you have properties and find out the weight 196.2 Newton. And then the centroidal radius of gyration, kg. So you have that here. And we can change that to 0.25 meter. Centroidal is centroid, and you see homogeneous body, so it will be also the mass center. The coefficient of kinetic friction, so that is kinetic, so you can see that in mu sub k basically, mu sub k, between the spoon and the surface, the ground, right, equal to 0.1. Determine the angular acceleration of the spoon when a couple C 30 Newton meter is applied as shown in there. Now this problem is a little bit tricky and it's a bit different from what we have done so far. So in the wheel, we can think about slip wheel, no slip wheel, but this one a little bit different when you have a cable here, right? So that is the cable that make big difference there. Assume we did not have a cable. It did not have a cable, so nothing in the cable. Cut that cable out of this system. If we apply the couple counterclockwise as you seen in here, if you can imagine, so the spoon tend to move to the left. Everyone see that, right? Now because it's grabbed with the around with the core here on that cable or the cord. Can we say the cord? Can change that to the cord. Then actually it will be making the spoon rotation and move to the right. Everyone see that? It's not normally, as you see, if it knows the cord, then it move to the left. But with the cord, it tend to move to the slide. So it will no slip on the cord so that the wheel can move to the right instead of the left. So have that intuition so that when you solve the problem with the positive, negative number, etc., you can be able to explain easier. So this is only one. So after classify motion, this body both rotation and translating. So it will be GPM, and you can see there. And property we already done. So the next one, it will be a draw diagram, right? So free body diagram only one, so we don't have to specify which body. So free body diagram equal to kinetic diagram, only one body, so we draw two. So two body, the same, two same body, one equal to circle equal to circle, spoon equal to spoon, and the center of mass is G. So let's break it G there. They should be the same. My one big, one small look crazy, but okay, let me redraw that one a little bit bigger. So they look the same there. Okay, so that's what you have. And then free body diagram on the left. So let's put down the weight, the way we forget, and that one is 196.2 Newton. And because that is inclined surface, no, that is the ground horizontal, so the normal force it will be vertical, and then the friction force, it will be friction FF. And then we have a couple clockwise, and they give us here C is 30 Newton meter, 30 Newton meter. And then we have a cable. We cut the cable, right? Isolate that body, cut that cable. So it will be at that point here. We have the cable. Go to the right T. Go to the right T. So let's give some geometry. That one equal to 0.4 meter. And that one here from the G here is 0.2 0.2 meter. Keep that in mind. And then on the kinetic diagram that we done for free body diagram, kinetic diagram, the body, like I say, it trying to rotate and translate to the right. So you will have MAGX, MAGX, MAGX. And in that case, M equal to 20, so we have 20 AGX. The center of mass G not jump out of the ground, it always parallel to the ground, which is horizontal. So you don't have MAGY. You don't have MAGY in that case. Because that all is about the center of mass. Center of mass keep maintain horizontal, no up or down. So that's why you don't have a MAGY. And then this body is rotation, so you also have IG alpha, and it go to the rotation clockwise, counterclockwise in that case, and you can couple counterclockwise. So here we can have IG alpha, IG equal to 1.25 alpha. And like I said, we don't have MAGX. So we done for the diagram, and then we just do the scalar equation. Let's do the y direction first so that we can find out the normal force. So sum of all the forces in y direction equal to MAGY. So from that we can have y, so we have n going up, positive, negative 1, 9, the weight, put 2. That's all we have on the left. And then right side, MAGY, like I say, G not moving up or down, so it's 0. So from that we can have normal force equal to, actually the weight in this case, 196.2 Newton. Newton. And then we have the sum of all the force in x direction equal to MAGX. So from that, what do we have in here? It will be, what will we have? We have, go to here, so we have tension in the cable, positive, normal force 0, weight 0, so it's negative F, subtract F, friction force. And on the other side, we have MAGX, in this case 20 AGX. So let's make that equation 1. Of course, that L, the first equation, we already find out N, so we don't need to care about that one. And then we have another equation, right? We have a moment. Sum of all the moment about G, about the center of mass. Why? Because that simplify your question. You can do another point, but the right side is more complicated in the kinetic terms. So let's assume, because it's rotate that, so counterclockwise, so we have that equal to IG alpha, and from that we can have couple, so we have 30 counterclockwise, so it's positive, and then we have friction force negative, so you have negative friction force times the moment arm 0.4 meter, normal force perpendicular and go through G, no moment arm 0, the weight go through G, 0 moment, T tension, so and it also clockwise, so it's negative, so you will have negative tension, and with the moment arm is 0.2, the inner radius 0.2 meter. So from that it equal to IG alpha, so it's 1.25 alpha, we have it in there, right? So 1.25 alpha. So that the two equation we have And let's see how many unknowns we have here. Right now. T1, 2, friction. Ag at 3. Friction already count. T already count. Alpha, that 4. 4 unknowns. 2 equation. So, see that? 2 equation. 4 unknowns. How can we do? Yeah, a few way you thinking about, right? The first one is draw another diagram. No, we don't have it. Only one body here. So that rule that out. The second scenario, assume something. That either on the right track, right? Because that is the wheel or the spoon sliding, slipping on the surface. And then the next one, as you can see, kinematic relationship. That also need to take into consideration. Okay, so those are the thing we need to do here. So, as you can see, go back here. The coefficient of kinetic friction between the spool and the ground is 0.1. So they don't give you the statics friction. They for a reason. As I explained earlier, this wheel will be rotation about the really that there are 2 points of contact in here. Let me write down here. You can see 2 points of contact in there because it can slide on the court or on the ground. But in this case, it go to the right. Then the real no slip, it will be at that PC. And it only give you the kinetic friction on the ground. So it will be sliding here. Sliding on the PC. This is PC1. Let's see that is PC2. It will be sliding at PC2 because the kinetic friction. So that it can be moved to the right. If it bow, no slip. So it stick there. It's static. So keep that in mind. So here we need to have a few equation and a little bit tricky in here. So let me write in red. Let's write in red. So as you can see, it have to be, they give you kinetics friction, right? So must, and it go to the right. So it, you see, must lie on the ground. Slide, must be sliding. Sliding at ground. And they also give you the kinetic friction. So from that, you can have the friction when it basically the wheels slip on the ground. So the friction equal to mu sub k. And for those of you forget about the slip, the difference between slip and no slip, we have a review. Go to note number 2. In force acceleration 1, you can see what are the different scenarios. So in here, mu sub kn, they give us a 0.1, right? 0.1 there. So we can put it there, 0.1, 0.1. And we already find out 196.2, 196.2. So from that, we can have friction force equal to 19.62 Newton. So we have one unknown done, right? One unknown. So that already done for FF. And then the next one is kinematic relationship. We need another equation because you have 4 unknowns. 4 unknowns there. Another equation is kinematic relationship. Any relationship between ATX and alpha. It's the same body. So, like I say, it have to be no slip on the court so that it can move to the right. So it's at PC1. So with that, when it no slip on something, then go back to the no slip wheel review. We will have acceleration at the center equal to alpha r. So what does that mean here? No slip at this point. At this point, no slip on court. So what do we have? The x center equal to alpha r. And the r in that case is here, not the whole wheel, because that is the point of contact that we are talking about. So this is the r we are talking. Make sense, everyone? Because that they slip, no slip on that point. So at that instant, the spool rotate about that PC1, not PC2. It's sliding on PC2, no slip on PC1. So from that, we can have another scenario. So very important to find for equation, because for known here. So it's no slip on cord, as I show you. So from that, we have to have a gx equal to alpha r, and r here is not 0.4, it will be 0.2 alpha, 0.2 alpha. So from that, we can have equation 3, and this is equation 4, and you have 4 equation 4 knowns. You can plug that in, so you can rewrite equation 1 and 2 like this one. So rewrite, I have equation 1 equal to t minus f already find out, so it will be 19.26 equal to, you see ATX equal to alpha r, so it will be 20 times 0.2 alpha. Okay, and then equation 2 we have 30 minus f minus t, so let's kick on the other side. So we have f times 0.4, so you have it 0.4. Simplify that, you can have it 30 minus 19.62, no, that's 19.62, 62 times 0.4 minus t times 0.2 equal to 1.25 alpha, and that 2 equation. Now you only have 2 unknowns, so that is 1 unknown here, t, and 1 unknown alpha. So 2 equation, 2 unknowns. You can see set up in the PDF, but just go ahead to solve this and then solve this, so you can find out the t equal to 55.2 Newton and alpha equal to 8.89 unit is radian per second square, and it will be counterclockwise. And the question asks is what is the acceleration of the spool? So this is the answer you have. So as you can see, it not only try the equation from the Newton's second law, but you need to have the kinematic relationship. So that one, as you can see, I just emphasize here, is a kinematic relationship. Very important to find more equation to solve. Otherwise, you cannot solve. So with that, we finish problem 2. Review very carefully. It's very good that have many concepts involved. So with that, we can move to problem 3.